they would give me something like what we see here. Sine x is equal to 1/2, and they would ask me to give all of the solutions between 0 and 2 pi for where sine was equal to 1/2. Now, we had two ways of doing this at that point. You could draw the entire unit circle if you wanted to and look at it and see where you had sine values of positive 1/2, and that was absolutely one way of doing it. If you've got 20 of these that you need to work, then you may still want to draw out your unit circle. But if you just have a couple of these to answer, remember we had the other way that we could do this by using reference angles. And so we've got our little first quadrant chart up here in the corner. For that first quadrant, remember that we have that little shortcut. If you start at 0 and count up, your numerators go 0, 1, 2, 3. And then same thing, if you start up here, your numerators count 0, 1, 2, 3. And then remember, this third value over here is our tangent value. We get that by doing the sine value divided by the cosine value. Pretty easy to come up with the multiples at pi over 4. But the value at pi over 6 and at pi over 3, remember, those are just reciprocals of each other. So once you find one of them, you can flip it to get the other one. That saves you a little bit of time. Excuse me. So if we have sine is equal to 1/2, and we're looking for the reference angle, we're saying where is sine equal to 1/2, and you can see that would be right here at pi over 6. That's going to be my reference angle. Then step number 2, we would say, where is sine positive? Because this was a positive 1/2, right? So then we would say sine is positive in the first and the second quadrant, and we would give the first quadrant pi over 6 and the second quadrant pi over 6. And something that we mentioned that was a way of kind of helping us figure out what that second quadrant pi over 6 was to use the idea that at pi, that's 6 pi over 6 or 4 pi over 4 or 3 pi over 3, whatever it is I'm dealing with. And so if I want to go 1 pi over 6 away from that into the second quadrant, that's 1 less than it. It's 5 pi over 6. If instead this had been sine x is equal to a negative 1/2, I would have been given third and fourth quadrant answers. And so to do that, I would have started at the 6 pi over 6 and gone 1 past that, which would be 7 pi over 6. Over here we've got 2 pi, that's 12 pi over 6. So if we do 1 less than that, that would be 11 pi over 6. So that would be how we could find those values. Now on the homework, and on most of the problems that we do, they're going to give me that stipulation of only give answers between 0 and 2 pi. However, in the examples in the textbook, they don't limit their domain in that way. They don't say only give answers between 0 and 2 pi. And so in the textbook, you're going to see them giving answers to the examples that instead of looking like this, they look like this, where they're saying like pi over 6 plus 2 pi n, or 5 pi over 6 plus 2 pi over n. Here's what they're saying. If I have to give every answer on the face of the earth, instead of just the ones that are within 1 revolution of the circle, then basically I need pi over 6 plus all of its coterminals, right? So the way I find coterminals is just add or subtract 2 pi. So we could go through and say, okay, if n is 1 or 2 or 3 or -1, -2, -3, or 0, that would cover all of the coterminals for pi over 6. So again, most of the time when we work, we're only going to be asked to give answers between 0 and 2 pi. But if they said find every answer on the face of the earth, then all I'd have to do is just tack that plus 2 pi n onto it at the end, and that would cover every other possibility. All right, so let's look at example number 1. Example number 1, they asked me to solve 2 sine x minus 1 is equal to 0. Now, typically when I'm solving an equation, I'm solving to get x alone on one side by itself, everything else on the other side, right? Well, you'll notice that x is attached to sine. So I can't just get x alone by itself. I'd have to use like an inverse sine and, get kind of crazy. If I want to find x, in a trig equation, what I want to do is get the trig by itself. I want to get sine, cosine, tangent, secant, cosecant, cotangent, whatever it is. In this case, sine of x. I want to get sine x by itself and everything else on the other side. Now, when we have been doing our trig functions, There are a lot of times that we'll substitute the trig function out. Like in this case, instead of having sine, we could say 2y minus 1 is equal to 0. If you had 2y minus 1 is equal to 0 and you were told to solve that, what would you do? Add 1 and divide by 2. So I'm going to do the exact same thing to this problem that we have. I'm just going to add 1 and divide by that 2. So let's do that. Let's add 1 to both sides and then divide by 2. And that is literally the only new thing that we're adding here, because you'll notice when I get here, I'm right back to where I was up here. So then I can proceed with what I already know, where I could either use the reference angle and the quadrants, or I could use the unit circle, whichever I preferred, to finish the problem. So the new thing for us today is solving that trig equation by isolating sine x by itself, getting everything else on the other side, and then continuing to solve. All right, look at the next one. Example number 2, I've got sine x plus the square root of 2 is equal to negative sine x. So I got to get sine x by itself on one side, right? So what you want to do? How am I going to get sine x on one side by itself? All right, let's add sine x to both sides. So I already had 1 sine x, so if I add one more, that's going to be 2 sine x. And then over here, when I added it, of course, it dropped out. All right, now what? All right, subtract the square root of 2, and then divide by 2. All right, so now I can go back to either look at the unit circle or look at this first quadrant up here. So where is sine equal to square root of 2 over 2? Pi over 4. And then where is sine negative? What two quadrants? Third and fourth. So I'm going to give the third quadrant pi over 4, which is 5 pi over 4. And I'm going to give the fourth quadrant pi over 4, which is 7 pi over 4. Now, when we were working with our inverse trig functions, we were doing some things that were very similar to this. When we were working with inverse trig functions, we were only getting one answer, right? We're back to giving two answers like we did back in section 4.4 when we initially learned this. We do not have the domain restrictions like we did with the inverse trig functions where I only use first and second or I only use first and fourth. I don't have any of that. If you'll notice, my domain is that I'm using from 0 to 2 pi. That's all 4 quadrants. So that's why we're back to getting two answers again. Something else is that you'll notice if I'm giving the fourth quadrant pi over 4, back when we were doing inverse trig functions, we wrote it as negative pi over 4 because that domain went from negative pi over 2 to positive pi over 2. That's not our domain anymore. Our domain is from 0 to 2 pi. So I don't want to write that as negative pi over 4. I want to write it as 7 pi over 4. Even though they're the same thing, I want to write it as 7 pi over 4. And we'll see that all the way through the lesson. We'll keep emphasizing that. All right, look at the next one. For the next one, we've got 3 tan squared x minus 1 is equal to 0. So I need to get tangent x by itself. So what you want to do first? Add 1. And then divide by 3. All right, so I still have tan squared. What undoes a square? A root, right. So I'm going to put in a square root. When you insert a square root, you always put with it plus or minus. Nice. So I'm going to insert a square root, and I'm going to put in the plus or minus as well. So the square root of tan squared is just going to give me tangent. And then over here on the right-hand side, the square root of 1/3, well, the square root of 1 is 1, but I'd have square root of 3 in the denominator. So I'd multiply top and bottom by the square root of 3 to rationalize. And we've done that same rationalization numerous times since we started our trig in chapter 4. Alright, so now I can go back up to my chart up here again. Even if you have drawn out the whole unit circle, Most of us on the unit circle only put the sine and the cosine values on there. We don't then go around and put the tangent values all the way around as well. You definitely could, but here's another instance why it might just be faster and easier just to use this first quadrant and to put those tangent values on. So in any case, where is tangent square root of 3 over 3? Pi over 6. And then where is it positive or negative? Oh, we've not seen that before. Where is it positive or negative? Well, where's it positive? First and third. Where's it negative? Second and fourth. So where's it positive or negative? All four of them, right. So I'm going to give all four quadrants. Anytime. It doesn't matter if I'm working sine, cosine, tangent, whatever. Anytime they ask me for where it's positive and negative, I'm going to give all four of my quadrants. And again, just emphasizing that we want to write it as 11 pi over 6, not negative pi over 6, because we're supposed to be giving answers between 0 and 2 pi. All right, first semester when we were working with solving regular algebraic equations, not anything trigonometric, but just regular algebraic equations, we talked about some dangers in solving equations. We talked about picking up extraneous roots when you multiply both sides by a variable, and we talked about losing roots when you would divide both sides by a variable. Here's an example of that. Let's say that I've got x squared is equal to x, all right? By the fundamental theorem of algebra, I know that the degree of the polynomial tells me the number of solutions that I'm supposed to have. So I should get two answers to this thing. If I go through in the first step and I divide both sides by x, that's a legal move in algebra. I haven't done anything wrong. As long as what you do to one side, you do to the other side, I'm allowed to do that. So I'm going to go through and divide both sides by x, and I'll be left with x is equal to 1. I got one solution. I'm supposed to get two. I lost a root. Anytime you divide both sides of an equation by something where it cancels on both sides, it's gone. You've lost it. And the same thing is true in example number 4. For example number 4, I made you a little caution out here. Do not divide both sides by cotangent x. If you divide both sides by cotangent x, it will cancel on both sides and it will be gone. Now, I'm not saying that you can never divide both sides by a trig function. The problem is it cannot cancel on both sides. Here's an example of where you could divide. Like, let's say that you had cosine x is equal to sine x. All right? If you went through and you divided both sides of this by cosine x, it cancels on one side, but it doesn't cancel on the other side, right? It's still there. Now I've got 1 is equal to sine x over cosine x. I started with one sine and one cosine, and I still have one sine and one cosine. But if I come up here to this problem and I divide both sides by cotangent x, it will cancel on both sides. It will not move. It will cancel and it will be gone. I'll be left with cosine squared x is equal to 2, and I have lost a root. Do you see the difference between those two? Okay, so I understand how I'm not supposed to do the problem, so how am I supposed to do the problem? Well, let's go back to that little example that we were using from algebra before we got to trigonometry kind of as a guide. Instead of solving that problem by dividing both sides by x, if I need to move that x and I can't divide by it, I could subtract it, right? So I could go through and subtract that x over to the other side. Then I would have a common factor of x. So I could take out my common factor of x, and then of course once I've got a polynomial factored, I can just set each of my factors equal to 0 and finish solving. And sure enough, if you notice, we get two solutions like we're supposed to when we do that. So again, I never want to divide both sides by something where it cancels on both sides and disappears. I've lost it, it's gone, and I will lose some solutions with it. So let's kind of follow the same pattern that we saw over here with our algebraic equation. Let's use that as a guide to help us over here with our trigonometric. All right, since I can't divide both sides by cotangent, let's subtract it over to the other side. So I'm going to subtract that 2 cotangent x over to the other side. All right, then, just as we saw in the algebraic example, we would have a common factor that we could take out. So let's take out that common factor of cotangent. And once I take it out, I can set each of my factors equal to 0. All right, so my left-hand side is simplified, but I can do a little more work over here on the right-hand side. What do I need to do to get cosine x by itself? Plus 2, and then square root. And, of course, when we put in that square root, we're going to put in a plus or minus. All right, so let's start with this first piece over here. Where is cotangent equal to 0? Well, remember the ways that we get an answer of 0 are when I am at those quadrant angles that are in between the quadrants, like 0, pi over 2, pi, 3 pi over 2, 2 pi. All right, so if I go through and I want to know where cotangent is equal to 0, I literally could go around and calculate the cotangent at each of those. There's a little simpler way to think about that. What's the definition of cotangent? Yes, you're both right. It is 1 over tangent and it is cosine over sine. I'm going to use cosine over sine here to help us out. What is the only way that a fraction equals 0? When the numerator is equal to 0. So if I want to know where cotangent equals 0, I could rewrite it as cosine over sine, and I could say where the numerator of that fraction equals 0, then the whole fraction will equal 0, right? So I could simplify where is cotangent equal 0 by thinking of it as where is cosine equal to 0. All right, so we could go through then and looking at our diagram over here, we can see that cosine is equal to 0 at pi over 2 and at 3 pi over 2. So those would be our two solutions. All right, then look at the second piece over here. Now we want to know where cosine is equal to plus or minus 1.4. Now, square root of 2 looks familiar in the beginning, but when I come up here and look at my chart, what I have is square root of 2 over 2, not just plain square root of 2. So if it's a value that's not on my circle, I'm going to need to throw that into my calculator. So remember, that's our Jeopardy button, right? When we know the answer and we're looking for the question. So we do second sine or inverse sine of 1.4 and second sine or inverse sine of negative 1.4. And when I do, I'm going to get an error message. Why is that? What are the largest and smallest values that cosine can be? It goes up to 1 and goes down to negative 1. So I'm asking it, where's cosine equal to 1.4? And it says nowhere. And I'm saying, where is it equal to a negative 1.4? And it's saying nowhere. The highest it goes to is 1 and the lowest it goes to is negative 1. So that's why if I throw that into my calculator, it's going to give me an error message. All right, look at the next one. For example number 5, they ask us to solve something that is in a quadratic form. So in order to do that, I'm going to factor. We have done this same type of factoring in 2 different sections prior to this one, kind of leading us up to this. So we've got 2 sine squared minus sine minus 1. Now, when we've seen this before, we've said if you want to, you can substitute this out. Like I could replace sine with x. So if I did that, this would be 2x squared minus x minus 1, and that might be easier to factor. And you are surely welcome to do it that way. We would like to get to the point, we keep seeing this over and over and over again, we'd like to get to the point that we can factor without always having to substitute it out just to save ourselves some time and energy, right? So let's try this one. Let's just try to factor it without substituting it out and see where we get. You always have the option of substituting it out if you want to. All right? So what would multiply to be 2 sine squared? Sine and 2 sine, right? Because the only thing that multiplies to be 2 is 1 and 2, right? And the only thing that multiplies to be sine squared is sine and sine. Okay, so that's going to be 2 sine times sine. All right, then down here I need something that multiplies to be negative 1. Not really a whole lot of choices there, right? What's that got to be? 1 and negative 1. And then I just need to figure out which one is going to add to give me a sign of negative 1 here in the middle. So I might need to play around with put the positive 1 here and the negative 1 here, put the positive 1 here and the negative 1 here, but a little bit of trial and error, and I can figure that out. And again, if you had factored this, you would have gotten 2x plus 1 and x minus 1, and then you would have put sine right back in the place of x. That's fine as well. Okay, so once we've got it factored, we can set each of those factors equal to 0. Look how far we've come today. This was like the first problem that we did today, right? And like just one of these itty bitty little baby things, and now it's like, you know, just the middle of another problem that we're doing. So, all right, so let's start over here on the left-hand side. What are we going to do to this guy? Subtract 1, and then divide by 2. And then this guy over here will add 1. All right, so now we're back to where is sine equal to 1/2? What's our reference angle? Pi over 6. And then where is sine negative? What two quadrants?
3 and 4.
3 and 4. So I'm going to give the third quadrant pi over 6, which is 7 pi over 6, and the fourth quadrant pi over 6, which is 11 pi over 6. And again, I don't want to give the negative pi over 6 because it's not in my domain. All right, let's look over here at this side. Sine x is equal to 1. We've gotten into the habit of getting 2 answers for every one of our pieces of these equations. So I don't want you to think you're doing something wrong if you don't get 2 answers. On the unit circle, the only place that sine is equal to positive 1 is at pi over 2. Because the alternative to that 3 pi over 2, it's negative 1 down there, right? So you won't always get 2 answers. Don't think you've done something wrong if you don't. So just pi over 2 for that piece. All right, look at the next one. For the next one, we have 2 sine squared x plus 3 cosine x minus 3 is equal to 0. So if I substitute that out so I can see what I'm looking at, I would have, I'm going to put y in the place of sine and x in the place of cosine. I'd have 2y squared plus 3x minus 3. I can't factor that as a quadratic. I can't factor a quadratic that has both x's and y's in it. And so I can't factor this quadratic that has both sines and cosines in it. I need a way to either replace y with x or replace x with y. Like I need it all to be x's or all to be y's. So same thing down here. I need this all to be sines or I need it all to be cosines. So I'm going to look at this and say, is there any way to switch cosine to sine? Well, no, cosine's just 1 over secant. I can't really switch that to something in terms of sine. But sine squared is a Pythagorean identity that we've seen. You can turn it around multiple different ways, right? Sine squared plus cosine squared is equal to 1. I could solve that, couldn't I? So I could go through, and if I take sine squared plus cosine squared equals 1, and I solve it for sine squared, I would get 1 minus cosine squared. So again, we've taken that Pythagorean identity and we've turned it around a bunch of different ways. It's in our notes multiple different ways. When we were working with verifying our identities last week, we wrote it numerous ways. So just that same idea, sine squared is 1 minus cosine squared. Now everything's in terms of cosine. Now I'm good to go. So I'm going to distribute that 2. So we did 2 times 1 is 2, and 2 times negative cosine squared is negative 2 cosine squared. I could combine my constants. I have a 2 and a negative 3, so I could combine those. Even when I don't have trig functions, when I just have a normal quadratic equation, I do not like to factor a quadratic when the leading coefficient is negative. I always go through and multiply the whole thing by -1 because it's just so much simpler to work with. So I'm definitely going to do that with my trigonometric quadratic. So again, just multiply the whole thing by -1, every sign changed. Alright, so now I'm ready to factor. And again, if you wanted to substitute this out, you could, but let's try and do it without substituting, okay? 2 cosine squared would have to be what times what?
2 cosine.
2 cosine times cosine. Just like over here, 2 sine squared had to be 2 sine times sine. 2 cosine squared has to be 2 cosine times cosine. Alright, then I need something that multiplies to be a positive 1 and adds to be a negative 3. So what do I need?
Negative 1 and negative 1.
Perfect. Negative 1 and negative 1. So then once I have it factored, I can set each of those factors equal to 0. So I could add the 1 and divide by the 2. And then over here, just add the 1. Alright, then I can look at that first quadrant and find where cosine is equal to 1/2. So where is that?
Pi over 3.
Pi over 3 then is my reference angle. And where is cosine positive? What two quadrants? First and fourth. So I'm going to give the first quadrant pi over 3 and the fourth quadrant pi over 3. And again, stressing that idea that even though 5 pi over 3 and negative pi over 3 are two different names for the coterminal, I want to give the 5 pi over 3, not the negative pi over 3. Just because they've told me to solve between 0 and 2 pi. Alright, how about over here? Where is cosine equal to positive 1? Again, we're just going to get one answer for this like we did where sine was equal to positive 1. But where's cosine equal to positive 1?
2 pi.
Alright, I heard 0 and I heard 2 pi, and you're both right. Cosine is equal to 1 at 0 and at 2 pi. But nowhere else today have we had to give two different names for the same answer, right? Like when I was given pi over 3 right here, I didn't have to say pi over 3 and then also give a coterminal for that where I said like 7 pi over 3, right? There's no need to give the same answer two different times. And if I were to say 0 and 2 pi, I'd be given the same answer twice. So I need to go back to that domain again. Every single time they're going to tell me find answers between 0 and 2 pi. And so that I know which one they want me to use, they put a bracket with the 0 showing we're equal to that, but they put a parenthesis with the 2 pi showing that I'm not equal to that. So I want to give 0 and I don't want to give 2 pi, again, just because of that domain.